let's learn about linear regression. Linear regression is a very important statistical technique which is used to predict a dependent variable y using an independent variable x. In this case, let's say you want to predict how much sales revenue you will get based on the advertising dollars that you're spending. Then you can model a relationship that says, hey, when I spend, let's say $10, I got $100 in revenue. And when I spent $20, I got $140 in revenue, and so on and so forth. So you get all of these blue dots, which is spending certain advertising dollars got you in the past sales dollars. So each of these are your data points. And so using linear regression, you can actually predict by building a model saying, hey, given any x value, what will be the y value that I will get? Meaning for any advertising dollars, if I can get the sales, I can do that. So the way you do that is a technique commonly used is ordinary least square, in which a linear regression model is built that builds a predicted line which minimizes the sum of squared distances from each of these data points with this line. So this line is basically your linear regression line that is going to help you predict what is the sales for the advertising dollars that you spend. Similarly, you could, and that relationship is called the simple linear regression. So the way you do that is you have your data points, which are all of these blue dots, right? And you say, I want to build a model based on these data points. And the way I want you to do that is look through within this data a column which represents the ad spend, which is one of your independent variables. Using ad spend, predict sales. Yeah? So build a model that can help you predict sales based on ad spend. So you have this data points that is a sales ad spend combo. Yeah, each of this data point is a point which represents how much money you spend on advertisement and how much sales you got. So using this data point, using ordinary least square technique, which tries to find a line which minimizes this distance from each of these blue points to this line, and if you add up the squared distances from each of these blue points with this line, it will be the minimum. Because you could also have a line that looks like this, but then the distances would be way high compared to this line. It will be much lower for this line because it is closely representing what the data is telling you. So that is very powerful. Given data, we can find out a technique which helps us predict sales based on ad revenue. Similarly, you could have many such variables that you can use as input, and you can predict your output y. Yeah. So when we build this model, we get the first parameter, model parameter 0, as the intercept, which basically tells us where is this line intercepting, right? It could be here, it could be somewhere here, wherever that is. So that's your intercept. Model parameter 1 would be the prefix to the ad spend variable, because that's what you're using as one of your independent variables. And you'll also get an r squared, model r squared. In this case, it's 0.8. So it's basically telling you that 80% of the variation in this data points is explained by this model. That's the key takeaway. Yeah. So what is it telling us? So it'll also tell us model.r squared. Model r squared of 0.8, which basically tells us that in our model, which is this red line, there is 80% less, 0.8 means 80% less variation than there is for a line that is the mean line. So let's say there was a mean line here, which represents the mean. So compared to the mean, this line here has 80% less variation, meaning it's much better. Model R squared of 0.8 for this data points that we had basically tells us that this model has 80% less variation than the variation around the mean. So each of these data points has a mean. You find out the variation around the mean, which is nothing but a line that looks like this, a mean line. Then the variation around the mean will be much higher, right, compared to variation around this line. So this model has 80% less variation than the variation around the mean. So it's good. So the higher the model R squared, the better it is. So the key thing here is, as you start adding more and more variables, your R squared will continually increase. That's why we also would want to use a adjusted R squared, because it will then penalize junk variables being added to our model, which doesn't really incrementally add the value of reducing the variation. Yeah. So that's model R squared. So you want to look at your intercept, your ad spend, and your model R squared. So you get all of this, and you can then have an equation that looks like this: sales equal to model parameter 1, which is your intercept, model parameter 0, which is your intercept, model parameter 1 times this variable ad spend. So now you can plug in any number ad spent, and you have these two model parameters that the model gives you. This will be some fixed number. This will be another fixed number. So model parameter 0 plus model parameter 1 times ad spent. This is a variable. So you plug in any ad spent, and with these two constants that the model gives you, you can predict sales. So that is super powerful. Let's say you never ran an experiment that had any number here between 20 and 30. You only ran an ad spend of, let's say, $20 and $30, but you're curious, what if I spend $25? So now your model will be able to tell you, you plug in 25 here, you use the constants that the model gives out, and you will get the sales output. So this is super powerful, yeah? We can now predict for any given x, any given independent variable, what's the output variable look like, your dependent variable look like. So now you can imagine, and the reason why it's called a linear regression is because it assumes a linear relationship between x and y, yeah? So you could also use, and that's a simple linear because there's only one independent variable that's used to predict the dependent variable. But if you have multiple independent variables, then we call it the multiple linear regression. Again, assumes a straight linear relationship. And in that case, what you can also do is you give it multiple parameters. Ad spend was one of those independent variables. You can also give it the customer income. Yeah, you could say, hey, which of these, and then you can give it customer income that basically says, okay, now you have two variables, two independent variables. And you can do the same thing. You could give the data points and then do a fit, and you will get, in this case, you'll get the previous parameters, which is your intercept, your ad spend, but you'll also get another parameter, which is the prefix for your customer income. Yeah. So now you can again create the sales prediction based on intercept plus the constant that we got for ad spend times the ad spend variable, another constant times the customer income. So you could take as many of these variables that you give it, it will be able to build a linear regression model, and it will also give you the R squared. We start to see that R squared continues to increase, was 0.8, now it's 0.88. It tells you that there is 88% less variation around this new model compared to the variation around the mean. But we have to start looking at adjusted R squared at some point when we start to see that, hey, there are a lot more independent variables being added, and you look at that, yeah? So in essence, this is our model. We are able to build this red line, which is this linear regression model, which is basically allowing us to form this equation, y as a function of various x's, in this case x1 and let's say z1, right? And allowing us to create this line, right? And the way it does it is, it starts off with, let's say, a line that looks like this, a mean line. It takes a mean data point and creates a line, and then looks at the distances, yeah? And then sums the square of all of those distances from this mean line, yeah? And then it says, oh, that mean line distance is, let's say, 100 units. and then it tries to change that line a little, so it will go to this line. And then it says, oh, the distance now is 80. So it's actually, this line is better than this line. And it keeps doing that. It keeps doing that, keeps changing the line until it reaches a line where the distance is, let's say, 30, and you cannot go below 30. So sum of squared distances, or OLS, ordinary least squared, it dynamically keeps finding out which line is better, and then it keeps going towards that line and optimizes towards getting that one line. Yeah. So R squared is variance around the mean minus variance around our regression model line divided by variance around the mean. Yeah. So in a sense, it's a super important technique for us to know what is the fit, how good is our model explaining the variance compared to just variance around the mean. So far we have looked at all of these continuous variables as independent variables, but you could also use categorical variables. Example could be like, what device are they using when they are seeing this advertisement? They could be using this mobile device with an iOS. They could be using a mobile device with an Android operating system. They could be using a desktop with a Windows operating system or a Macintosh operating system. So let's assume you only have these four variables, and that are like your categorical variables. Yeah, you cannot like just add up and say, hey, the mean iOS number of users. Yeah, you will have to look at each of these as categories. And so the way it's represented as within the model is, the model looks at categorical variables and creates dummy variables. In a sense, it tries to find out prefixes for each of these variables, categorical variables. So in this case, we can see that it will create prefixes for iOS, Android, and Windows, but it skipped one, desktop, Macintosh, because you can infer the fourth one. If these three exist, right, there will be one of these at a time. So let's say they are seeing this advertisement on mobile Android, then this will be 1, all of these will be 0. Yeah? If all of these three are 0, then it's easy to infer that it's a desktop Macintosh. Yeah? So it's able to find out what dummy variables to use for a categorical variable. If it's within your data, if you give it categorical variable, and then you say, hey, that's one of the variable is a categorical variable. In this case, if you replace ad spend by what device type they are using, then all of a sudden it will create many more parameters based on how many unique types of values are there in your categorical variable. So that is, in a sense, linear regression, a very, very powerful technique to help us predict what is the impact of an independent variable on dependent variable and how we can predict it. You can start to imagine you can use this for so many ways. You might have like earnings of a stock, and you want to predict stock price movement. You might have hours spent on studying for the exam, and you want to look at exam scores. So you can do so many real life things by looking at what is the impact of X on Y, and you can start to build a prediction model that tells you how to predict for any given X, what's the Y. There are some things you need to be careful about. We talked about R squared versus adjusted R squared. There's also like data cleaning that's probably needed, and there's going to be lots of outliers. In this case, I gave you blue dots that were like, very linear, but you might have outliers somewhere here. And so what you want to do is you want to really look through whether there is indeed a linear relationship that you're fitting in that makes sense, or if you want to transform your data and actually then fit a linear relationship, or you may not even want to fit a linear relationship if there is a higher order relationship possible. You want to clean your data, you want to start looking at overfitting, and there are many various other techniques you would want to start looking at once you understand the basic concept. And most of these libraries, OLS, Stacks Model, Python provides a lot of these out of the box, so you can use these libraries to start building prediction models. So super, super powerful. Understanding dummy variables that are used for categorical variables, understanding how we can have multiple variables that are used, understanding the importance of R squared, understanding how to extract the model parameters, and understanding how to build a machine learning model. In this case, it's a simple linear regression model that learns how to represent your data, and it allows you to predict what's going on, yeah, in terms of capturing the relationship between, in this case, ad spend and sales. So super powerful. We will go into more advanced topics in the future videos. That is also super important to build, but this is a brief introduction to linear regression on how it works and how you can get started. Thanks.